Okay, in this lesson today, we're going to take a look at linear, quadratic, and exponential relations and determine if we could try to find a way to match up a graph, a table, and an equation and truly prove that they are equivalent and they all match together. So you can see here on the screen, there's one parabola, so that's a quadratic. There's one that looks like it just rises real quickly. That's our exponential. And we've got one just straight line. That's linear function. And underneath it, there's four different tables. And underneath that, you're going to see five different equations. We're going to try to match these up to the type of function that they are, but also not only just saying like, oh, this is a linear equation, so it goes with the line. We're also going to look at, well, how do I know that this specific linear equation goes with this specific line? Because let's say, for example, there was another graph right here that looked slightly different. Say it was right here and it was like a lot steeper or something like that. Or sorry, not as steep. And it looked a little bit different. Well, how do you know that this equation truly matches this graph? So that's our focus of this lesson. Be able to determine a way to figure out, are these all truly equivalent to one another? So let's take a look at the tables first. Looking at these tables, we got some X's and Y's, a whole bunch of different sets of them. And we've got some graphs, and you can see very defined points. I mean, they all kind of stand out very well. So you can see some defined points happening here, kind of all over the place. Ones that we could try to match up our table to our graph. Now, what you don't want to do is just match up one single point. And here's the example of that. This is a parabola. This is a quadratic. So let's look for a table that maybe, and it doesn't have to be this way, but maybe the values, the y values start off high, then maybe they come down, and then they rise again, right? Because that's like what parabolas do. So this first table right here starts at a value of 8, then the values decrease to 4, but then increase to 8. The next one is just a constant increase, increase. This one goes down to -3 and then increases after. So there's only two that looks like it could be just based on the initial. But let's actually test points. So this is the point 0, 5 right here. All right, so that's the point 0, 5. Well, if I look at my four tables, 0, 5 takes place right here and right here. So the question is, can I stop and say equivalent, right? These two tables match this one graph. Equivalent, check mark, we're done. No, it does not work that way. We got to actually prove it. We got to show that it takes place with more than one point. You should have at least 3 points that you should be able to identify. So let's go to the next one. Let's see here, 1 comma 8. Well, if I go to 1 and I go up, that's 6, 7, 8. Yep, 1 comma 8 is right there. Well, this is 1 comma 12. So that definitely does not match. This one does not match what we're working with. So this 1 comma 8 does match. Test one more. -1, +4. -1, +4 is there. We can say that E and L are equivalent relations. They match each other, okay? So those two are connected. Let's do the next table. So E and L go together. The next one looks like exponential. Well, we saw previously that exponential tables tend to have like a doubling factor or a tripling factor, or maybe they're being cut in half from one value to the next. So let's look at these two. 1, 2, 4, 8, 16. Hopefully you guys are recognizing that that's being doubled every time. 2, 4, 6, 8, 10. Well, that's just 2 being added constantly to it. So what should stand out is that R matches up with the exponential 0, 1, 1, 2, 2, 4. Each of these points are matching up. R matches up with Q. So we've got these two as a match, and we have R and Q as a match. And then this one was linear because it's constant, +2, +2, +2, +2. But not just that it's linear, it truly matches this graph because I can also see my points match. So 1 comma 2, the inputs and outputs, the x's and the y's of the table match the x's and the y's of the graph. So that's how specific you have to be with your language. You can't just say they match. Like, how do you know they match? What is the equivalent statement? Well, the x's and y points in my table, the inputs and the outputs of my table, match those that of the graph, okay? So we can see that these took place as well. These are points that we can confirm. So we can see that these, and I'll just kind of try to code it for you, just doing different shapes, underline circles or some triangles. Those match as well. Well, that means this one's out, right? This table did not match anything. We can cross that one out. There is no match for this one. And that's okay, because what you would say is this is not equivalent to one of the above. The x's and y's in this table, the points, do not match the points in my graph. And that you could stop right there, right? So let's take it a little bit further and see what we have for our equations. So the equations now, we have to try to see if they match. And we could do it a couple different ways. Here's where you have options. Because we already know that R and Q are a match, well, if we were trying to look for an equation that matches that, we could try to match up our equation with either R, the graph, and figure out a way to determine equivalency, or we could say, let's determine if this table matches this equation. Because if R and Q are equivalent, well, then if we find the other equation that matches either R or Q, that means they're all part of the same group, right? So we've got options here for how we want to do this, and you just got to get comfortable with that and try to figure out, well, how do I know if they match up? Okay, so let's continue. Let's do the linear and the exponential first, because those are the easiest to be honest. All right, this is a linear equation, 2x. This is an exponential equation, 2 with the exponent of x. Okay, so we see that that's linear and that's exponential. We see linear here, and we see exponential here. But the question is, are these truly equivalent? Just because it's linear does not mean it matches this specific line. Okay, so you got to actually test it. So what you should do whenever you're given the equation is you should create your own table and see if it matches the points on the graph or if it matches the points in that table. So here's the equation, remember f of x, that's the same thing as y, right? Let's create our own table. And let's go, 1, 2, 3. Let's see what happens. You got to test minimum of 3 points. You can't just do one, okay? Minimum of 3. Let's plug in these x values right here, 1, 2, and 3. Let's plug them into this equation, and whatever we get back are the y values. So plug in a 1 right here, right, lost the pen, right here for x, right there. So it's 2 times 1, 2. Plug in a 2, 2 times 2, 4. Plug in a 3, 2 times 3, 6. Well, does that match our table we saw? 1, 2, 3, 2, 4, 6? Yeah, it does. So we know now that this truly is a match. These two go together. It's not just that it's linear function, it truly matches it. And we can say that they are equivalent. So let's get another triangle around this one. Let's do the same thing with the exponential. So this exponential here is y equals 2 to the x. Whenever you see the equation, you should create your own table and test minimum of 3. So let's do 0, 1, and 2. Let's see what happens. Plug in a 0. 2 to the 0 is 1. Plug in a 1, 2 to the first is 2, and plug in a 2, 2 squared is 4. So double check, 0, 1, 2, 1, 2, 4. They do match. We know that that is also part of the, and truly equivalent to the exponential ones right there, okay? So now we got to get to our quadratics. We can tell that these are all quadratics. These 3 because of the exponent being a 2. So x squared, squared, squared. But we need to see if they're equivalent. I'd say the easiest way to do this is to look at these and say, okay, this is standard form multiplied out. This is standard form. This one right here is vertex form. So it's in a different format. It's a lot easier if they all look the same. So let's actually do some distribution like we saw last class. Let's multiply this all out. and then see if it actually matches one of the two that are there. So let's multiply this out. Let's see here. We learned that we should expand this. X plus 3 times another x plus 3. Write it twice. That's what the squared concept is. Do some distribution right here. Multiply this all out. I'll just draw the arrows of where these are coming from. X squared, 3x, 3x, 9. Don't forget about that minus 4. X squared, 6x, minus 5 by combining like terms. What do you notice here though? These right here, and I'll relabel this P, these are actually equivalent. They don't look the same, but when you do the distribution, they're actually the same exact function. So you can't just assume oh, they look different. They can't be equivalent. No, you got to actually check it. So this turns out to be the same exact thing in a different form, equivalent forms of an expression. That's what we're working on here in this unit. So we can already say that this one here, P, is equivalent and a match to D. So those two both match. What we want to now check is, does this match our graph that's up here? Right? Does that truly match our graph? And remember what we tried to do. If you're ever given an equation, you create your own table. Okay? So let's create our own table and see if it matches the table that matches the graph that we already found as a pair. So let's take this right here, go off to the side, create our own table. So I'm running out a little bit of space here. And let's do, what did we say again? -1, 0, and 1. Those would be three good ones we could use. -1, 0, and 1. What you have to be really careful with when plugging these in for our quadratics is this squaring idea. Okay, I need to take these x's right here and plug them in. So for -1, I need to plug it in right here and right here, simplify it down, and see what I get as a number. But what happens a lot of times, and I see this happen all the time, even though we know what it is, -1 squared, which is -1 times -1. Off the top of our head, we can all do that, and we'll say that that is +1. -1 squared is +1. But what I see too many people do is rely on their calculator, and they do this on their calculator, -1 squared. And then they hit enter, and it's going to give them back this answer, -1. That's not right, okay? And it's not like the calculator's messing it up. Who's messing it up is the individual who is not typing it in correctly. If you're going to square a negative, you need to put that -1 in parentheses. So just be careful with that. I see a ton of mistakes with that, and then it would truly give you the correct value of +1. So just be very careful. So let's check. -1 squared is 1. Where's my pen here? There it is. So -1 plugged in right here. 6 times -1 plus 5. -1 squared is 1. And then 1 plus -6, or 1 minus 6, we're at -5. And we add 5, and we end up getting 0. Plug in a 0, and we end up getting back 5. Plug in a 1, and we end up getting back 1 squared plus 6 times 1 plus another 5 is 12. That doesn't look like it's matching up with what we saw here in this table, does it? -1, 0, 0, 5, 1, 12, but take a look at this. Didn't we cross this out earlier? Uh-oh, looks like we have a new match. Let's use a square. This equation, which is equivalent to this equation, actually matches this table. So there's no graph that matches with it, but we found another equivalent pair there. So we're able to determine, based on what we were able to plug in for our table, that there's actually another match. Okay, so let's check this last one and see if we can get a match out of this. X, Y, let's do -1, 0, and 1. -1 squared is 1. 1 minus 2 is -1 plus 5 is 4. 0 plugged in here and here gives you back just a 5. 1 plugged in here and here gives you back 8. -1, 0, 1, 4, 5, 8. We found our final match. There it is. And we know that this equation right here matches this graph and this table. So this section has a lot to it, a lot of content, where we're trying to focus on how could I know linear, quadratic, exponential? Am I able to distribute properly to determine two equivalent equations like P and D? Can you do distribution? Can you create your own tables in order to determine, does this equation match this table? And can you recognize the difference between all three? All right, so a lot going on in this video, but that is the whole concept of this section: equivalent forms of relations and finding equivalent forms and different forms of functions.